Well, hello friends, welcome back to the show. Today we are going to look at compiling performance in Serenity because that was one of the pain points when I was making the last video developing inside Serenity. So I have a very simple little test program here. It's just a Hello World GUI app basically. And if we build that app, you can see that it is not particularly fast, especially linking seems to be really slow, but it does work. It does produce a running application, and I think if we run again, then it's going to be a little bit faster the second time because things are in cache. But really, this performance is pretty atrocious, and today we're going to be investigating why linking is so slow in particular. So if we only do the link command here, seems like time doesn't play well with this because he gets confused thinking this option is for time. That seems like an oversight in the shell implementation of time, but ignoring that, we can still see the time over here. So the linking takes 2.2 seconds. And it's just a dead simple app that we just saw, right? This shouldn't take 2.2 seconds to link. So let's work out what's going on. So we run, we add -v to get the command that's actually being executed. So I think this is the one right here. Let's put that in a text editor so we can look at it. So collect to, I suspect we can just replace this with LD because it looks like an LD invocation, right? So let's see if that produces a binary that we want. It does in 1.4 seconds. Okay, so I guess maybe collect to is doing something on top of that. I'm not sure. But even so, this is still pretty slow. So this should be profilable. That's where I want to get to. Okay, and then let's take a look at the profile. So this is the linker running on our little program here. And the time is spent in read block. Okay, so reading from the file system. Looks like the read syscall is about 52% almost, and the write syscall is 26%-ish. So reading and writing I/O is totally dominating linking. Okay. So maybe let's look at writing first. Time is spent in ext2fs, write bytes, and then we have to resize the inode. Okay, so I guess it's like writing out the file incrementally, and as it does that, the file keeps growing, right? So we have to keep resizing the inode. And that is expensive apparently because Blocklist for inode. Wait, resize. Okay, so in the file system, every inode has a list of blocks that make up the content of the file, right? And when we resize an inode, we go and fetch the old block list and then add to it, I guess. That doesn't seem like it would be super necessary though, because we normally cache the block list for an inode. So if you're at the point where you're resizing an inode, I think you should probably already have a cached version of it, of the block list. So let's see, resize calls out to write block list for inode. Sure. And write block list for inode. Wait. Am I in the right place? No. This is back up. Resize calls block list for inode. So this is to retrieve the current block list of the inode that we're about to resize. But I'm pretty sure that we have it cached. So that would be something like, what is the block list? It is a vector of block index. Block index is not a thing. ext2fs block index, yeah, there we go. And if we have a block list, then just use that. Wait, what am I doing? M block list. So if it's non-empty, use the existing block list. Because we have this, every inode caches the block list associated with it, but I guess maybe it's lazily populated. Let's see, we do this at the end of resize. We will assign a m block list, and during write bytes we assign a block list. So whenever we write to a file, we will do this after resize though. Oh, interesting. So how would we even be here with an empty block list if we've just called resize? I'm not sure that makes sense, but ignoring that, create inode will also do this. So I guess it's only when you open an existing file and then we lazily populate the cached block list. So let's see. Block list. Yeah, so if we have a cache block list, we'll just use that instead of generating it on the fly here, because I think we'll probably hit this cache all the time and completely get rid of this time spent. So let's test that theory. So 3.3 seconds full time, cached 2.9, that's very good. And I should have saved that command we were using. Just a linking step. Let me get that out. Yeah, we can put this in a file or something. Go. So 1.1. That's definitely an improvement. So let's see if we can get a profile of that. Okay. And what does it look like now? Read is up to 64%, and write is down to 10.5. So definitely an improvement. Definitely an improvement. So I think it's unavoidable to spend some time and write. We can probably improve that further, but I would say this is already dodging a whole bunch of work that we already have done anyway. So let's commit that. use the cached inode block list in and resize if available. If we have already cached the block list of an ext2fs inode, can save a lot of time by not regenerating it. Yeah. Okay, that's great. And then let's extract that command. Go summon. Okay. Oh, right. Yeah, so that's pretty good timing, but I bet you we can go way faster, so let's take a look at this. Fresh profile. Because we haven't really been trying to optimize disk I/O in forever, so it's probably something really obvious we can do here. So we're doing a bunch of reads, which go into inode file read, sure, and then all of the time sort of disappears into block-based file system read block. But if we flip this around, you'll notice that it doesn't look like we're spending any particular time in the hard disk driver itself. So we're hitting the disk cache pretty hard. So block-based file system has a disk cache. It's right here. So every file system that is based on some kind of underlying block device will cache the most recently used 10,000 blocks. And when you call, for example, block-based file system read block, and of course caching is allowed, which means that I think if you pass odirect to open or osync or something like that, then we bypass the cache. But assuming that you are using the cache, then read block will go and get the block index from the cache, and only if it's not cached will we actually hit the actual physical disk, right? Of course, this is abstracted here because the block-based file system operates on a file descriptor, because you don't see the actual device interaction here, because you can make a block-based FS on top of any file, as long as it's able to serve you block-sized chunks. Anyway, this cache here is definitely not very strong, so I think we can probably improve that dramatically, because the disk cache, it's one per block-based FS, as I was saying. So you can see here we have in block-based FS, which is the base class of file systems like ext2fs. There is a disk cache home putter. So we just instantiate one of these in, I guess in here probably. Yeah, so the first time you try to access the cache, we'll just make it. And the way the cache is laid out is that it's one large buffer with all of the cached blocks, and it's another buffer with the entire table of cache info. And it is a large array. So it's a big array of cache entry structs. This is it. Like, it's 10,000 of these structs laid out sequentially in memory. And when you try to get something from the cache, then we will just walk the cache from 0 to the size of the cache. And this is not going to be particularly fast if you since you have like 10,000 entries and you have to scan the entire 10,000 entry array every time that you do a block read. Of course, you'll stop early if you find it, but worst case scenario, you have to scan the whole thing. So we can probably make this substantially faster by just adding a hash map like in front. And I think the reason I didn't do that originally was because hash map, well, for one thing, we were limited by a statically sized kernel heap, which is no longer a problem because it's dynamically sized now. And also the hash map data structure in the ACK library was particularly crappy in that it would do a heap allocation for every new entry. And it has since been rewritten in a video I did a while back. So the hash table data structure is now like one big allocation instead of multiple disjoint allocations. Anyway, long story short, let's see if we can just add a hash map here. So instead of walking the cache entries, we would have a hash map from U32 to U32, I guess. So it's just basically from a block index to a cache entry index. And it's tempting to use like a U16 or something here, but let's use a U32. Let's say map. Yeah. And then when you look for something in this cache, let's see. So you come here, and then what we'll do is it is map find block index. So if we find it, we can do it this way actually. Then that means that we should be good here. So let's see. Let's make one of these. And then let's assert that the entry block index is the same as the block index that we're looking for, just to validate that our fast lookup map is working right. And then wait. Here we are updating the timestamp. I guess, yeah, this is to make sure that we track whenever an entry was last used, because if we read a block from disk that was not in the cache, then we want to put it in the cache. Then if the cache is full, then we throw out the least recently used block. So that's why we have to keep track of the timestamp. This thing is actually very unoptimized. I mean, obviously, as you can tell from what we're doing right now, but I think it's silly that we would need to scan the entire thing to find the least recently used entry as well. We could keep track of that separately, but let's do one thing at a time here. So, so this is if we have it in the map, then we'll return it quickly instead of having to scan. If we do have to scan, now, actually we should never find it if we have to scan, so we can assert that the entry block index is not block index because it should have been found by the map lookup. And here we're just keeping track of what is the oldest clean entry. Yeah, so we're essentially like looking for where to insert here. And I think we're gonna need the oldest clean index instead of the entry. So let's write it this way. If oldest clean index doesn't have a value, then oldest clean index is I. Okay, and then if not, oldest clean index has value, then yeah, so the cache was completely full. Then we make sure that we flush any pending writes, because it's not just that it was completely full, but it was also completely dirty. And the cache has a dirty bit for every entry, and if an entry is dirty, then we can't evict it from the cache because it differs from what's on disk. So before we can get rid of a dirty entry, we have to flush that entry to disk, and then it becomes clean and we can recycle the slot for a new incoming entry. So here, entries. Dot. Wait, what? What is entries? Cache entry. Oh, dot value, right. Because it's an optional. Okay, and then so this will become our new entry. I guess we have to const cast here. Whatever. Okay, and then now that we're replacing the oldest clean entry, we have to actually get rid of whatever was there before from the cache. So I mean from our map. So m map remove block index. I guess if new entry has a block index, then we will remove it from the map. Let's just mark it mutable. Jeez. Okay. If this entry occupied, remove previous mapping from fast lookup table. Okay, and then I guess we'll want to insert a new mapping here. So set block index that we're looking up and point that to the oldest clean index, which is the new index that we're using. Mapping from block index to this entry. Okay. So let's test this out. That immediately failed. Entry block index is not block index. Okay. We're failing here. Wait, is this because it's 0? I mean, we read a whole bunch of things from disk here. Wait, let's see. Let's just print them out. it was very loud. Okay, so we're looking for block 0 and it was block 0. Okay, so they're all pre-initialized to 0, which is a valid block index. So I guess that screws us up a little bit. So we can't strictly rely on block index 0 to mean that it's block index 0. So I guess we should say like bool is used, like as long as it doesn't grow the struct 20 bytes. Yeah, it doesn't grow it, so it's all good. Assert entry is either not used or they're different. Yeah. True, and then they become true the first time they become used, and we are good. Okay. So 3 seconds uncached, 2.4 cached total, but oh, look at that. 320 milliseconds. Right, now we're starting to get somewhere here. 633 milliseconds. 307. 307. Yeah. That's really fast. Nice. So let's profile that. And where is the time spent now? Yeah, the read and write IO is like gone from the top of the profile here, which is very cool. And we have to go all the way down to here. 6% in read, down from like above 50. That's very good. So which syscalls are now dominating here? I guess, okay, so total 25% in syscalls, but it's a much more reasonable distribution. We have read, unmap, write, mmap, and open. So it seems like this was hugely helpful. And actually, let's just verify that the program still runs. Yes, it does. Okay, so that that hash map made the block cache significantly faster, which is really nice. And we could do more improvements here, because it's kind of sad that like as long as you're hitting the cache, you're good, right? But like when you miss, then you have to walk the entire cache to look for which replacement entry to use. And yeah, we could improve that too, but let's not get carried away here. Let's just commit this, I think. So kernel, add a fast hash map, a fast lookup table to the block-based fs disk cache. Instead of locking the whole cache, instead of doing a linear scan of the entire cache when doing a lookup, now have a fast, nice O1 hash map in front of the cache. This dramatically improves disk I/O performance. I should say it's not disk I/O performance, cached disk I/O. cached file system IO. Yeah. That's very nice. The cache miss case can still be improved. This patch really only helps the cache hit case. Let's see. Yeah, because I guess you could keep track of what is the oldest entry somehow, so that you don't have to scan to find it, and then you get rid of this walk here as well. But that's really kick-ass. So do we even have any other things here to look at right now? Like all of this stuff here looks like internal linker symbols, right? Like they're not Serenity code. You can tell because they're C symbols. fread file. So fread, yeah, but it's going to be spending the time in the kernel mostly. It looks like we are spilling a little bit of runtime in the libc layer, but nothing to cry about, I think. Kmalloc. Kmalloc. I feel like something is not completely right with the profiler. Like, there are things missing somewhere, and I'm not quite sure where. But regardless, we're not going to get into that now. But something is off with the profile. Like I feel like I'm missing the innermost frame or something like that. That is weird. Anyway, this is looking very good. So if we just split open this thing here. So it looks like there's 60, like 2/3 of the runtime is in lang process, which I assume is like the reading all the input for the linker, and then 1/3 is writing, presumably. I don't know if that is a typical split for a linker, but it seems kind of reasonable to me. Open inputs, load symbols. Yeah, I mean, it's just a linker doing linker stuff. Okay. So we're not gonna try to optimize the GNU linker today. I was just interested to see if there was something standing out somewhere here in these top functions, but walk wild. That is a cool name for a function. Anyway, let's see, how fast is a incremental rebuild here? It's 2.2 seconds to do a full build. And when we started, it was above 4 seconds, so pretty good. Yeah, and then, of course, compilation is another step that needs to be optimized as well. Oops. How long does this take? 500 milliseconds to compile like this tiny little file. That's obviously too slow, but I think we're not going to get into that today because we already got some good stuff done here. Anyway, this is going to be it for today's video. So we got our little cache fix, and also we take advantage of the fact that inode's already cached our block list, so we don't need to recreate it. Altogether, that was a huge improvement, so very nice. So yeah, as I said, this is the end of the video. Thank you very much for hanging out. I think this type of stuff is absolutely necessary to make Serenity livable as a development environment. So I'm really glad that we spent some time on this, and I hope that you found some of it interesting. And if somebody has some good ideas about how to improve file system caching performance and stuff like that, I would love to hear about it, because I don't know anything about it. I'm just approaching it from first principles, as always. Anyway, thank you very much for checking out the video, and I will see you next time.